Welcome to the 14th lecture in general topology. The topics that we will explore in this lecture include additional properties of local bases, a continuation of our study of the ordered topology on the reals and the rationals, and an introduction to the subspace topology. Okay, so we'll start with the first exercise from the previous lecture, and we'll state it as a theorem. So let X together with some topology tau be a topological space. Let X be a point in the space, and let script B sub X be a neighborhood basis at the point. Then the collection script C sub X, consisting of the interior of the set B for every set B in the neighborhood basis, is a local basis at the point X. So proof: as script B sub X is a neighborhood basis, at the point X, we have that for every neighborhood U of X, there exists a set B in the neighborhood basis that contains the point and is a subset of the set U. Further, as each set in the neighborhood basis is itself a neighborhood, of the point X is in the interior of the set B, which is a subset of the set B. That is, for every set in the neighborhood basis, the point X is in the interior of that set, which is a subset of the set B. And so for every neighborhood U of X, there exists an element which is the interior of a set B in the collection script C sub X, which is the set of all such elements, where B is in the neighborhood basis, such that the point X is in this set, which is a subset of the set B, which in turn is a subset of the set U. And hence the collection script C sub X is a neighborhood basis at the point X, all of whose members are open sets. And therefore the collection script C sub X is a local basis at the point X. So given a given a neighborhood basis at a point, we can easily construct a local basis at the point. Okay, so the second exercise we will also state as a theorem. Let script B be a basis for a topology on a set X, and let X be a point in the space, Then the collection script B sub x, consisting of all basis elements which contain the point, is a local basis at the point. So proof. Let U be a neighborhood of a point in the space. Then that point is in the interior of the set U, which is a subset of the set U. Now, as the collection script B is a basis for the topology, on the space X, we have that the interior of U, which is an open set, is a union of some basis elements further. Every set B sub j in the union is a subset of the union and therefore a subset of the interior of the set U. Now, as the point X is in the interior of the set U, the point is in the set B sub j for at least one index j in the indexing set. Now let script B sub x be the set of all elements in the basis that contain the point. Then, for every neighborhood, U of x, there exists an element B in the collection script B sub x such that x is in this point, or rather in this set, which is a subset of the interior of the set U, which in turn is a subset of the set U. And hence, the collection script B sub x is a neighborhood basis at the point X, all of whose members are open, and therefore the collection script B sub x is a local basis at the point X. So, given a basis, we can construct a local basis at any point in the space. We can also do the opposite, that is, given local bases for every point in the space, we can construct a basis for the space, and we'll state this as a theorem. So let X together with some topology tau be a topological space. Let X be a point in the space, and let script B sub x be a local basis at the point. Then the collection script B, which is the union of all local bases for the points in the space, is a basis for the topology tau. So proof. Notice that the collection script B, which again is the union of local bases for all the points in the space, contains all the elements in the local bases, which is all of the sets in the local bases for every point in the space. Now, as each local basis at the point is a local basis at the point, we have that every set in the local basis is open, and hence the collection script B is a collection of open sets. Now let U be open, and let X be a point in set U. Then there exists an element B in the collection script B such that X is in this set, which is a subset of the set U. That is, for every open set and for every point in that set, there exists an element in the collection script B, which is a collection of open sets such that the point is in this set, which is a subset of the set U. And therefore, the collection script B is a basis for the topology tau. Okay, so the third exercise from the previous lecture I'm going to break into two examples. So first, as an example, consider the rationals in the order topology. Now let X be a point in the space of rationals, and let U be an open neighborhood of the point X. Then there exists an open interval in the basis for the ordered topology on the rationals such that the point X is in this interval, which is a subset of the open neighborhood U. Now notice that the intersection of the open interval with the complement of the singleton containing the point X is the intersection of the open interval with the union of the open ray from negative infinity to X with the open ray from X to positive infinity, and this is the union of the open interval from A to X with the open interval from X to B. Now, since A and X are both rational numbers, A plus X divided by 2 is also a rational number, such that this rational number is in the interval from A to X, and hence the intersection of the open interval from A to B with the complement of the singleton containing the point x is not empty. And so for every open neighborhood, u of x, the intersection of that neighborhood with the complement of the singleton containing the point x is not empty, since every open neighborhood contains an open interval which intersects the complement of the singleton in the space of rationals. And hence, every point in the space of rationals is a cluster point. Of the space, and thus there are no isolated points. Of the space. Now, since the space of rationals in the order topology is T2, it is also T1 or Fréchet. And since it is also true that every point in the space is a cluster point, this means that every non-empty open set U in the space contains infinitely many points. Of the space, since for a T1 space, a point is a cluster point if and only if every open neighborhood of the point contains infinitely many points of the space. Further, every finite point set F is closed, and so the interior of the closure of F is the interior of F, and since there are no non-empty open sets contained in a finite set, the interior of the finite point set F is empty. And hence, every finite point set is nowhere dense. In the space of rationals in the order topology.